As a quick review, we've breadboarded the entire Breakout arcade game to learn how each circuit works. Then we created and tested our own retro board. Now we're stuffing all that circuitry into an ICE40 FPGA using the Arduino 3.1 module. We're using Visual Studio to create Verilog files for each section and wiring them all together in our top-level main file. The main module's ports connect directly to external pins, and we're using buffers and circuitry to bring in switches, buttons, and controls, and to drive audio, video, LEDs, etc. The Retro KiCad schematic is nicely sectioned, so we're using that. So far, we've coded the oscillator divider, video counters, sync, and borders from sheet 1, the flip screen logic on sheet 4, and the paddles on sheet 2. Today we're back on sheet 1 building the ball XY counters and ball motion controls. We're not getting deep into the circuit operation here. You'll need to go back to the breadboarding videos for that. The ball counters are straightforward, basically a pretty close copy of the video counters, as they should be, except with the ability to slightly advance and retard the ball counters via bias lines to create motion. You can see part 8 for more details on how the ball stuff works. For inputs, we have clock and XY load bias lines. For outputs, we have the ball signal plus a few frequency pick lines for sound. The frequencies of these outputs are the exact same frequencies coming off the video counters. There may be a few more or less cycles per frame from these, but the frequencies are equivalent. The reason these tones were taken from these counters is because they're right ass up against the sound one-shots. We can make a decision to take these off our existing video counter buses or still peel them off here. Since the reason they tapped these was physical, I'm good with just using the vertical counter lines when we do the sounds. If that doesn't feel right to you, you can modify this to export them from here instead. This section uses 4 7161s, a couple of 3-input ANDs, and a NAND gate. Let's create a new file for this and add the I/O parameters. We're going to need a load line for the low order counter bias values. We'll drive that later. We need 4 74161s, copy the parameters and prep one of those. We need the TC line from every counter, so I'll add a loose wire for that. Make 4 copies. We're not exporting the XY counters themselves, so we'll need to create buses to hold those values for use within this module. Wire up the low order X counter. Looks like we have an extra copy. Get rid of that. Wire up the high order X counter. Wire up the low order Y counter. Wire up the high order Y counter. Create the ball signal by combining those 2 3-input AND gates. And finally add the logic for that load line. Save that. Back to main. Instantiate that. And wire it up. We'll need a loose wire for that ball output. Let's just set the X bias values to slow/right and the Y bias values to slow/down. Save that. We need to temporarily drop our new ball signal onto the video sync section so it shows up on screen. There it is. We'll also need to keep it out of the syncs. Save that. Compile and upload. Looks like those counters are working okay. Here's something stupid. Let me repurpose those two push buttons and hook them up to the bias lines. I'll create separate wires for P2 conditional and attract. Modify those. And the PCF file as well. This is stupid. Let's just make those generic. Now modify the bias values depending on button state. You can use the ternary operator to create an implicit selector mux, just like in code. Let me default attract mode to on so we have a visual box. Save that. Compile and upload. Yeah, stupid but kind of fun. Next up is the motion control, so I'll create a new file for that. Before we get into the real circuit, let's make our own cheap motion control like we did for the breadboard. We'll need the raw ball signal, top, pad, the left and right hand sides, and we'll just put out the X and Y load bias values. We'll simply use two set reset latches to drive the load bias lines, but first we'll need to go make a simple SR latch. Well, that should work. Add two of those and wire them up. Now I need an output wire. We'll change X direction appropriately when the ball hits the top or paddle. We'll then change Y direction when the ball hits the left or right sides. Set the load bias lines to the proper slow values for each axis. Add that new section to main. Copy the parameters. Add buses to hold our emitted load bias values. We've got ball and pad, but we'll need to go back to the borders section to get top, LH, and RH. We forgot to export top bound when we made this, so we can just add that now. We'll also temporarily export the sides for our cheap controls. Back to main. Add wires to hold those outputs. Yeah, wire them up. We can now use the load bias outputs. We need to invert that pad line. And that needs to be an assign. We can get rid of the sync suppression on ball as well. This is still temporary until we get the ball display line from the serve logic later. Oh, those sets and resets are active low, so fix that. We'll still hook attract to button 1, but invert it so attract mode is on for this test. Also hook P2 conditional back up to the other button. Nah. Yeah. Save that. Compile and upload. And the ball stays within our box. Always a good thing. I guess I could have used medium speed. Okay, let's back that fake crap out and go do the real circuit. There are 4 distinct parts to the motion controls: X motion, Y motion, the volley counter, and the speed up circuit. We'll create 4 submodules in our motion control file. We'll need P-Sync, B-Sync, V-Sync, ball display, top bound, brick hit, serve weight, SBD, 16 Henry, 16 Victor Prime, PC, PD, and P2 conditional. She then puts out the X bias lines, the Y bias lines, and these 3 hit lines. Let's work on the X motion submodule, which takes in P-Sync, ball display, top bound, B-Sync, brick hit, serve ball detect, P2 conditional, and X0. She puts out down, X1, X2, BP hit, BTB hit, and this line that steps the volley counter when the ball moves away from the player. This section uses just 1 flip latch and a bunch of gates. Here we've run into our ICE 40 issue where their latches only support a single set or reset, and we need both. There were a lot of suggestions on how to overcome this limitation, but what worked for me is this thing that uses 3 latches and a mux. On initialization, all Q outputs are low, so the bottom latch is active and its state flows through. When the set line asserts, the top latch becomes active, and when the reset line asserts, the bottom latch becomes active. Any clock data flows to the active latch. I'm sure this can be done in other ways, but it's what worked for me, so let's add this thing to the gates file. We already created a D-type flip-flop with set and a D-type flip-flop with reset. Oh, that set one doesn't. Fix that. And we just made an SR latch, so we have everything we need to make this full-body D-type flip-flop. Add the parameters. Add the top set type latch. Add the bottom reset type latch. Add the SR selector. And finally assign the output through a mux. Back to the ball motion file, add the X motion submodule, and add the parameters. Still a lot. Add our everything bagel latch and wire it up. Yeah. Q connects directly to VC step, but it feels more intentional to make a separate wire for the output since it's used a lot here, like this self-feedback line for flipping direction when a brick is hit. Yeah, we need to generate those hit lines, so let's do that first. SBD here just forces the ball to move towards the player on serve. And finally wire up the rest of the outputs. Now we actually need to instantiate the XMotion submodule within the motion control module. So let's copy the signature. Add loose wires for the outputs. Oh, forgot to add the real ball motion ports. Add those now. Yeah, that's a lot of ports. Now we can wire up XMotion. We don't have X0 yet. That comes from the volley counter. The starting volley state for X0 is high, so I'll just temporarily tie that up. We need to add the real parameters to main, so copy those. We can just replace all of this. And wire it up. We don't have ball display yet, so we'll use the raw ball signal. We don't have brick hit, serve weight, or SBD, so tie those appropriately. We also don't have PC or PD yet. And we need wires to hold those hit lines too. In the ball motion section, we're not driving LX or LY from anything yet. LX would normally be assigned to X2, CX1, and CX0, but we don't have CX1 and CX0 yet, so we'll use the base values. We don't have Y motion done yet, so we can just set LY to slow/up. Well, we don't have X0 yet either, so like before, we'll pull it up to its default value. Save that. Build and upload. The ball should bounce back and forth in the X direction and just slowly float up in Y. Yep, as expected. We need that Y motion, so let's go there next. This section takes in BP hit, PC, PD, VSync, BSync, 16 Victor prime, and VSlow, and puts out the Y bias lines and VB hit. The bottom direction latch operates differently than in our cheap version. Here they check if the ball runs into VSync, checking 16 Victor prime to see if it was the left or right hand side. 16 Victor prime is off when the ball hits the left side and on when it hits the right side. We went over this detail in Part 8. This section uses a simple data-only flip latch for the top deflection angle latch and a full-bore flip latch with set and reset for the bottom latch. Add a Y motion module to the motion control file and add the parameters. Add the top latch and wire that up. Add the bottom latch. Wire up those intermediary parts. And finally emit the Y bias value bits. Copy those parameters and instantiate within the motion control module. Build and upload. The ball should now bounce off VSync and stay within the box. Yep, works as expected. The next section is the volley counter. This takes in the VC step signal from the X motion controls, serve weight and speed up lines, then puts out just X0 and V slow. X0 and V slow then adjust the X and Y speeds as volley progresses. We'll also emit the raw counter outputs for display. This section uses a 74193 up-down counter and a couple of gates. Not sure why they didn't use a 74161 here, since it just uses an up counter. We don't have a 193 yet, so we need to go off and make one of those first. Now the 193 is tricky because there are 4 synchronous control lines, and we can only check 2 things in an always block with the ICE 40. In a situation like this, we could use a high-speed clock for the always block trigger, then track control line state changes between clocks and take the correct actions. Since I don't want to add a separate clock here, we're going to raw dog this one from the datasheet circuit. You can see that they use 4 T-type latches with set and reset inputs. A T-type latch is typically a JK flip-flop where asserting the T clock toggles the output, hence the T. We're going to use 4 of our full-featured D flip-flops and connect data into the inverted output to create the toggle when clock rises. This circuit is set up so the T clock for each bit is only asserted when you want that bit to change. Bit 0 is easy. On either an up or down, you simply toggle the output. No questions asked. That makes perfect sense from a binary perspective. For the remaining bits, you need to check the lower order neighbors before deciding if you should flip. For up operations, you only want to flip if all lower order bits are on, because it's your turn in the binary count sequence. For down operations, you want to flip only when all lower order bits are off. For bit B, for example, if we're doing an up and A is on, we need to flip, so the clock is pulsed. For bit C, we check to see if both A and B are on before flipping. And for D, we check C, B, and A. Down operations follow basically the same pattern, but check for lower order bits to be off. The carry and borrow outputs use this same principle to chain devices. Now the clear and load operations, on the other hand, use the set and reset inputs. A clear operation simply pulls down all of the reset lines while prohibiting potential set assertions from a load request. And finally, the load operation asserts the set lines, but only for data bits that are on, and asserts the clear for data bits that are off. That's why clear and load operations occur on the front side of their respective pulse, and count operations occur on the back side. I'll stop talking and wire that up. Save that. Oh, that's all nice, but I really want to test this. So I'll temporarily add one to main. Use the buttons for up and down, add a loose bus to hold the output, and shove that through the first 4 debug bits. I'll stick a hex display on those. For some reason, the compiler complains about using D, so I'll change it to DAT. I'll look into that later. Oh, I forgot to wire up the D output. Seems to work nominally. Remove that crap. Back to our ball motion file and add the volley counter definition. I'm going to export the volley counter value as well so we can display that. We'll need one of those 193s and a couple of gates. Not using the carry and borrow outputs, but we still need to add them. X0 and VSLOW are simply inverted counter outputs. Now instantiate it in the motion control module and wire it up. Need a couple loose wires for the outputs. We now have VSLOW and X0, so we can wire those to the Y and X motion circuits. And we can use X0 in the bias value. No, we don't have the final CX lines yet. Better. I'll need to add that volley counter output to the motion control definition to export the value. Then go back to main and add that to the instance. Need a loose bus for that output. And hook it to the debug port. Missing the periods here. You know what? Let's also add a temporary test input wire and hook one of our buttons to it to test the speed up line. We'll need to add that to the definition as well. Then hook that test wire up to the SU input. Save everything. Compile and upload. Didn't break anything, and you can see the counter step when the ball switches direction away from the player. I say it this way because the volley counter also steps when the ball bounces off the back side of a brick. You see our normal progression where X goes to medium speed at 4. Then back to slow at 8 while Y goes to medium. Then X goes back to medium at Charlie. Pressing the button should load Fox, which it does. That doesn't change anything here because only the 2 upper counter bits are used and didn't change. If I restart this, then press the speed up button, it immediately jumps to max. So that's all working. Okay, last section for today. The speed up circuit takes in brick hit, 16 Henry, serve weight, down X0 and X1 and puts out SU and the proper CX0 and CX1 bias lines. She just uses a D-type flip-flop with reset and a couple of gates. 16 Henry is low when the ball hits a high-value brick, causing this latch to be set. Add the new speed-up module to the ball motion file. Add the parameters. We finally get the SU and CX lines. Add the proper flip latch and wire it up. Need that output wire. Change my mind again on the parameter name. And finally wire up those outputs. Instantiate that in the ball motion control module and wire it up. We'll need a few loose wires for those outputs. We can now hook SU into the volley counter and use CX0 and CX1 in the X bias lines. Don't need to define here since we have the actual wire coming in. Forgot that comma. We brought in the positive version of that. To trigger this, I'll temporarily hook both brick hit and 16 Henry to a button. 16 Henry needs to be low for a high order brick. Save that. Compile and upload. Simulate a high value brick hit, and voila, immediately jumps to fast. So that section's working. One thing we forgot to test from the X motion controls is the brick hit line. We don't want to be hitting a high value brick for this test, so I'll revert that 16 Henry input. Actually, we don't want to accidentally hit a high value brick for this test either, so I'll force that off. I mean on. The X motion latch is set up to flip the output when the clock rises. Simulating a brick hit reverses the ball direction and steps the volley counter when the direction changes away from the player. Cool, works fine. Alright, a long one today. At least we can easily type in wires instead of physically adding them to the breadboard. Now that we have a ball, we need to hit some bricks, so we'll do that next. Thanks for watching.